Okay, page 3 of the I/O notes. So what I showed you on the previous page was how you can turn on and off certain bits in a control register, and that will control the behavior of the I/O device. So that's a typical way of interacting with it. You can also read the status register and examine individual bits to see, what's going on with the thing. Now, one thing that I bet you are dying to know is how does this LPC underscore UART arrow operator IER correspond to the address that I said that the interrupt enable register was at, which is hex 4000 C004. So how does that happen? Well, I'm going to tell you. The first thing you need to know is that there is a struct. So there's something called the LPC underscore UART underscore typedef. If I had been naming this thing, I just would have called it underscore T, not underscore typedef. This is a struct, and it is found in this header file, lpc17xx.h, which we include in our projects. And so now what we're going to do is we're going to go and look at the there's a handout for this, so I'm just going to reference the UART struct handout in the notes here. So we're at the home page, click on content, then go to lectures and lecture handouts, and going to download the UART struct handout. This is the entire struct. And I told you before there's somewhere in the range of 20 to 30 registers on the UART, and either the struct doesn't have them all or I lied to you. I think that probably I lied to you. So if you count them up, there's about, I think there's 14 there, ignoring the reserved things that show up there. So this is a fairly complicated struct compared to what we're used to seeing, and if you look there, you'll see that there is a union here. So that I introduced the concept of unions back in the last lecture topic section because I knew we were going to see them here. So what I'm going to do is I'm going to show the memory layout of this struct. And I want about 20 rows, something like that. So quite a few. Hopefully that's enough. And so this struct is going to be, when you create an instance of it, like say you malloc it or you declare a variable of this type, it's going to be in memory at some starting address. And each of the parts of the struct are a certain offset from the top or the start of the struct. So we have a byte offset here. And so the first element of the struct has a byte offset of 1, or sorry, 0, and then 2, 3. So I'm showing this byte by byte. (14, 15). I'll stop at 19. I'll probably expand in a little bit. And so the receive buffer so we got a union there, and what it does is it overlays 4 different things: the RBR, the THR, the DLL, and this reserved thing, starting at the same memory address. The first 3 are all just 1 byte each, but the third thing, that reserve 0, is 4 bytes. So this is going to go from offset 0 down to offset 4, and so those 4 are labeled reserved 0. So that's that uint32 type. And now at offset 0, what we have is the RBR as 1 byte in size. We also have the THR overlaid in the same memory location, and the DLL. So the RBR is where you read receive data, the receive buffer register. THR, the transmit holding register, is where you write data that you want sent out the serial port. And the DLL is for setting up the clock, and we're totally not going to deal with that in this course. Now, I discovered another error in what I was showing you in the previous section, and it's in the next union. Down here, we've got the DLM as 1 byte, but the IER is actually 4 bytes. So the IER is 32 bits. So what I showed you on the previous page, I was showing 8 bits. We were just looking at the lower 8 bits. Still kind of valid what I showed you. The DLM, again, is for setting up it's some kind of phase lock loop timing thing. So anyway, we're not going to worry about that. But the DLM would be this byte here. So what this reserve 0 does up here is it makes us set aside bytes 1, 2, and 3, so we don't try to put the DLM or the IER starting at that register. The interrupt enable register, since it is 32-bit register, it needs to be aligned to, it needs to be naturally aligned. It needs a memory address that's a multiple of 4. So it can't start at offset 3 or offset 2. It needs to start at offset 4, 8, or so on. So that's why the reserve 0 there is kind of, it's used to force the padding that we need. We could have relied on the compiler to insert the padding, but by using that reserve 0, it makes it explicit. And then we've got, so first union, second union, the third union combines 2 things. This IIR, which I don't remember what it is, it's not too important, and the FCR register, which is 1 byte that starts there. So it's kind of weird to have registers at the same memory address, but that's not uncommon with hardware. If you read it, you're reading one, when you do a read operation on the bus to that memory address, you're reading one register. If you write to that address, you're writing to a different register in the I/O controller. And then it can also depend what mode the controller's in. So if you're in the setup mode, then you might be writing to the DLL instead of the THR, for example. And so after the third union, we have an 8-bit or 1 byte register, the LCR, the line control register, which is at offset of 12. And then there are 7 bytes that are set aside as reserved. So that should take us to the end of byte 19, 13 to 19. So there we've got an array of 7 bytes, so that's reserved 1, and I want to add 2 more rows to this diagram. Not going to do the whole thing. So there's 20 and 21. So after the reserved 1 comes the LSR, the line status register, and the line status register is another byte-sized register. And then after that comes reserved 2, and so on. So, too much detail, right? But this is how you can define a struct that allows you to address different register in an I/O device's interface without having to use like the magic address. You can assign a name to it, which is a good thing. Okay. Lastly, you can see right in the first union here, we've got 3 different prefaces. These are type specifiers in front of the uint8 type double underscore I, double underscore O, double underscore IO. So it's saying that the RBR is an input register, THR is an output, and DLL is input output. There's no such thing in C as double underscore I, double underscore O, and so on. These are type defs from another file, but I'll show you that in the notes. So let's go back to the notes. You've seen the struct now. And so then what we do is we create a pointer like this. So LPC underscore UART underscore type def. That's the type. We're going to create a pointer. We call it LPC underscore UART. And we set that equal to a memory address. And in this case here, the memory address is the base address for all the registers. So they start at this address 4000C000. Now, that's not going to compile just like that, because that is an integer literal, and that is a pointer to one of these, to the UART type def. So we need to cast it. And we can do this two ways. Probably the more proper way is this: LPC underscore UART underscore type def pointer, cast it to the kind of pointer it is. If you didn't want to write all that, instead you should be able to just write void pointer, so it converts the integer literal into a void pointer, which can be implicitly cast to this LPC UART pointer type. So now we've assigned our pointer to the base address. So we assign the struct pointer to the IO device base address. And so then when we do something like this, LPC underscore UART arrow operator IER, this adds the IER byte offset. So if you go back to that handout, it started at an offset of 4 from the top of the struct to the struct address, and that gives you 400 C 000 plus 4. Whoops. C004. And that is how, if you go back to our question at the top of the page, that is how we get that address using that code.